Good day, I'm Neil McCord. Today we're going to discuss the effect of power, frequency, and skin effect on current carrying rods, pipes, and channels. This is an AC magnetic simulation using QuickField 6.6 field simulation software. I'd like to thank Vladimir Podnos and the folks at QuickField for helping me with QuickField and this presentation. To give you a little background on myself, for over 40 years, I've been designing circuit breakers, switches, and other switchgear devices. I have over 28 years on the PES switchgear committee, where I've been the head of a few standards. I'm a senior member of the IEEE and the ASME. High voltage substations have many conductors in them. They're generally aluminum, they're open air, and we're going to be looking at the current distribution of them. A particular example that I'm highlighting is a air disconnect switch where you can see all of the components. You've got the bus conductor, the switch blade, which are both hollow tubes, and you've got it's common to have a channel as the jaw and hinge for the conductor. Plan for this analysis is to start, we're going to model the skin effect in different shaped conductors. We'll start with a round bar, then a pipe, a flat bar, then a channel, and in the end we will contrast the effect of the different shapes. It is the intent of this presentation to focus on the properties of the block and edge labels, post-processing, and understanding the meaning of the results. For good reference on the physics of the skin effect, please see the QuickField proximity webinar by Dieter Stotz. Anytime I perform an analysis, I like to start by stating the given. It's 2000 amps, frequency of 0 and 60. QuickField requires a depth with the AC magnetic plane parallel models. We're going to use 1000 millimeters, and the conductor is aluminum, 6063. 52% conductivity is 3 times e to the 7 Siemens per meter, and the relative permeability is 1. And these are the shapes that we're going to model: the 2 5/8 round aluminum bar and a 2.5-inch Schedule 80 pipe have very similar outer diameters, but not exactly the same. This is the geometry model of a round bar. On the next slide, we're going to show how the model was created. In this video clip, we're going to discuss how to create the models shown in this presentation. I'm going to show how to make the simple rod. I tend to turn on the properties, that way I can look back later and see that I've got the correct properties when I'm evaluating the results of the analysis. So I opened the problem. I can open up my geometry, I can zoom in and inspect the mesh, I can look at the results, I can zoom in and inspect the results, compare them to the legend on the left of the screen. At this time, I'm going to close this file and show you how to create it from scratch. To create a new file from scratch, you open the problem, you name the problem, and it comes up default in mine. In electrostatics, yours may default something else, but we're doing AC magnetics. I'm working in millimeters in this model, but I'm using an North American 60 Hertz frequency. LZ is the depth in and out of the paper. It's common in and out of the screen. It's common to leave that at 1000 millimeters, 1 meter. So there are several ways to input the geometry. One way is to use insert vertices and edges, I like to use insert shape. Sorry it's not showing up on the screen, but it will. So for insert shape, I'm going to start by putting in a circle. My circle is 73 millimeters, centered at 400. 400. Insert, and then I want to put a rectangle centered at 400, 400, and the size is 800 by 800. Close the insert shape. I like to go for a zoom to fit. At this point, we've got all the geometry I used. So let's identify the, let's create the block and edge labels. So for the edge, you select one, hit Control, select the other edges, hit the right button on the mouse, go for properties, and we're going to call this edge. We're going to call that, with the right button, I've selected this, and the properties are air. The block label is air. In here, I've selected the conductor, and I'm going to call it COND for conductor. Pretty easy at this point. You've got these questions, and it's best to answer them. The permeability of air is 1. That's described a little better in a slide coming up. The permeability of the conductor is 1. The electrical conductivity is also explained in the presentation 301. 1, 2, 1, 2, 3. 3 in Siemens per meter. And for a field source, we're going to be defining the current, and the current in this case is 2000 amps. And we select that. At this point, we're in pretty good shape. We need to define the edge. The magnetic potential at the edge is 0, which is also described in the slides as to why. So here we can build the mesh. That was fast. I did forget to open up the properties. Like I said, I like to save them. And all we have to do after we make the mesh, come over here, hit solve. It's solved in 1 second. I have a fairly fast computer. And that doesn't look like a good FEA. If you look at the mesh itself, the mesh is rather large and clunky, and that's pretty much how the post-processing looks. So to fix that, we go here, solve and refine. Refine the mesh 1 time. You can see the mesh is much better. And truth be told, that's pretty good, pretty smooth, but I see a few little issues. It only took a second to solve, so I'm just going to do this again. And you can see the mesh is even finer, and it's solved. And there you have it. One other feature I will show you here is that when you're looking at the results, you need to examine the variable, what these colors mean. You can push the field picture properties button, and you can read the maximum is 797 amps per meter squared, and the minimum is 188 amps per meter squared, which is actually the same numbers you've got here. Sometimes I like to look at this just to double check. Another way you can examine is to add a contour. You pick just outside that straight line and draw it right to here. And now you can look at an XY plot. This shows the current distribution. And you can also view a table of all the data, which can then be brought into Excel or something. So this is how I did the analyses. In the previous slide, I show you a video of how to create the models. As I said then, I will explain the models in a little bit more detail here. You can see that I've selected the boundary as given it a magnetic potential of 0. This is just free space. You will see here that we're picking the block label properties for air, shown here, here, here. Relative permeability of air and aluminum are 1 and 1. I've picked out the definition of permeability here from Wikipedia. I find Wikipedia to be a very useful and helpful tool. Again, here we are looking at the block properties of the conductor that are here. 30 billion Siemens per meter for 6063 T6 aluminum. Again, I've picked is the conductivity, and the field source is 2000 amps. The electrical conductivity and conductance is the reciprocal of electrical resistivity. You can see that I've picked this out of Wikipedia, very helpful resource. In Wikipedia, the answer to this is different because it's generic aluminum. We're using 6063 aluminum as stated in the slide above, where I put the given values for the analysis. Here we're looking at the solved solution, and we've got 3400 to 3.373 to 3.400. You'll notice that at 0 hertz, the resistance and impedance match, and the current is very evenly distributed. Here, I've changed the frequency to 60 hertz, and you can see that the current is not evenly distributed, as will be shown in the next slide. I've also picked up the resistance, impedance, current densities, power losses, and energy densities. Notice that at 60 hertz, the resistance and impedance do not match. This is due to the skin effect. It's very nice, as I showed you in the video, how you can get a distribution of the current. Most of the current is concentrated on the edges due to the skin effect. Power loss is similar, but not exactly the same. Now, what's very important to know in our field is that pipes carry about the same amount of current due to the previous graph as rods do, and they cost less and they weigh about half as much. So here we have a 2.5 inch Schedule 80 pipe. This analysis was performed at 0 hertz, calculates the resistance and impedance matching. Here we've got a 2.5 Schedule 80 pipe performed at 60 hertz. You can see the resistance and the impedance are quite different again. Current density is actually fairly consistent, and the power losses are pretty consistent. I've had to circle the current density plot because it's just way up at the top on the two outer edges. It's fairly consistent. Power loss is a little different shape, but similar. This slide shows the current density of the rod versus the pipe. So all of the current that would normally be in here is put in here. And you can see that we've got fairly even current density where the middle of this rod isn't carrying much current considering its cost and weight. Previous Excel graph was made by copying the table from the post processor from QuickField directly into Excel. Please note that all of the data is in one table and you got to pick out what you're looking for. The positions, the joule heating, the amps in watts per meter, the Siemens, all these things are in here. And the temperature doesn't mean anything because we haven't put in any, we're not calculating temperature in this. Here you can see that we're looking at a flat bar. This is a common shape in not so much in high voltage, but it's a very common shape in low voltage. And we're actually not covering voltage here. This is simply AC magnetics and current. So in this one, we're going to look, the frequency is 0. The current distribution is fairly even. And we've calculated this resistance, the impedance, the current density, and the power loss. You can see here that when we change to 60 hertz here, the current distribution is very different and extreme, and these values are different. Now this is a common shape in substations in high voltage air disconnect switches. So I've put this in here to see how the distribution is. Here we have a zero frequency plot. Here we have a 60 hertz plot. You can see that the current is pushed all the way to the top. Now you always have to be careful. Just because this is dark blue and this is hot red doesn't necessarily mean that there's a big difference in the current. But clearly when you look, it's an order of magnitude. From 2.24 e to the minus 5 impedance changes to 1.56 e to the minus 4. Quite a big difference. And you can see the current distribution is higher here, but it's not quite as dramatic as the straight bar. I want to pause on this slide a little bit. This is important. This is what I've been getting at with everything else. I've copied the impedance in air. This is the impedance of the rods and pipes in air. I've altered the frequency 0, 60, 0, 60, rod, pipe, and the impedance. And because this chart is a little, you can see the 6, 4, the minus 5, but the chart's not so clear. But the graph makes it very clear that at 60 hertz, the impedance is much higher than the 0 hertz, which is really basically DC. So the resistance, the impedance at 0 hertz equals the impedance at 0 hertz. From this, you can see how the impedance increases at 60. Well, what does this mean in the real world? For this slide, we're showing the contrast of the 2 5/8 round bar versus the 1.5 inch Schedule 80 pipe under AC current at 60 hertz. These are basically the same outer diameter, not exactly the same. You can see in the left view that the resistance and the impedance are different because of the 60 hertz, but you'll notice in the right view that the resistance is a lot higher, but the impedance is actually a very small amount lower. This is due to the AC current at 60 hertz. When you take the conductance and the weight per foot into account, you can calculate that the pipe carries the same current as the round bar with only 44% of the weight. For your time, I'm Neil McCord. I'm a consulting engineer. If you have any questions or would like my help with any issues, please feel free to contact me at neil.mccord@ieee.org. Thank you very much.